Hello everyone. Uh, in today's lecture, we will continue solving exercises related to the duration and the convexity topics. Remember, last time we have done exercise number 2, and it was about how to measure duration and convexity, right? Now we'll move to exercise number 4. The good thing with the number 4 is that it summarizes practically all that we have seen about duration and convexity. We will see that, or we will do once again the computations of convexity measures and duration measures, and then we will use them in order to estimate the price change in bonds whenever there is a change in the bonds yield, right? So we will see that duration and convexity are not just useful to assess the volatility of the bonds price, but also they are useful in order to estimate the future change of bonds price following a change in the bonds yield. So let's start and let's go to the exercise number 4. Our exercise number 4, page 90, right? So actually, we will use the same data that we already have used in exercise number 2. So we'll consider the bonds A and B data, right? So as you can see here, for bond A, it is offering a coupon rate equal to 8%, a yield to maturity of 8%, maturity of 2 years, par value of $100, and the current price is also $100 since the coupon rate is equal to the yield to maturity. Now for B is offering 9% coupon rate, 8% of yield to maturity, a maturity of 5 years, a par value of $100, and a current price equal to 104.055. See that the current price is higher than the par value, and it is due to the fact that bonds B is offering a coupon rate higher than the yield to maturity. Now, for the fourth exercise, he's supposing that the yield to maturity will grow up by 100 basis points, and he's asking to calculate once again the current prices of A and B with this new data, or with this new assumption that the yield to maturity will increase by 1%, which means the yield is no longer equal to 8 but 9%. So let's start. So we'll open a new Excel file, right? We rename the first sheet as question 1. So we'll dedicate a sheet for each question. Now let's start by the bond A. Okay, so first of all, we have to remember the data that characterizes the bond A. So we have first the coupon rate, then the yield to maturity, then the maturity, and the par value, right? So A is offering 8% as annual coupon rate. Now the yield to maturity has increased, so it is no longer 8% but now 9%. The maturity is still equal to 2 years, and the par value is still $100. So in order to compute the new actual price for bond A, we'll use the conventional discounted value technique which means that the current price of bond A will be equal to the present value of its expected future cash flows. All right, so let's build a table. So the first column is for period, the second one is for the present value factors, the third one is for the cash flow offered by the bond, and the final one is the present value of these future cash flows. So since the bond is paying semi-annual, coupons, this means that the periods should be, converted from annual to semi-annual. So, and since we have 2 years of maturity, it will become 4 periods or 4 semi-annual periods. So the first one, the second, the third, and the fourth period. Now the present value factor, as all of you know, is equal to 1 divided by 1 plus discount rate power the number of period, right? And discount rate here is the yield to maturity, but you have to pay attention. This one is the annual yield to maturity, so it has to be converted to semi-annual. So it will be equal to 9% divided by 2. So this is the semi-annual yield to maturity. So present value factor is equal to 1 divided by 1 plus, see, power the number of periods. So 1 divided by 1 plus the semi-annual yield to maturity power the number of periods. See, now the yield to maturity will be constant all over the maturity of the bond. That's why we have to keep it constant. So all we have to do is just to add the dollar sign to the reference cell, and that's it. And we can scroll down and we have the remaining present value factors. Now the cash flow paid by the bond is equal to the coupon payment, which is the par value times the coupon payment, the coupon rate, sorry. Now once again, we have here the annual coupon rate, so it has to be, first it has to be converted into semi-annual coupon rate, so equal to the annual coupon rate divided by 2. Then the coupon payment is equal to the par value times the semi-annual coupon rate, and it will remain constant for the second and the third period. But for the final period, the bondholders will receive, sorry, so B63, sorry, so once again we have to fix the par value since it is constant 1, right? And we have to fix also the coupon rate. So every time we are dealing with fixed number or with constants, we have to put the dollar sign. So once we scroll down, we should have now $4 as coupon payment. Now for the final period, in addition to the coupon payment, we will receive the par value. So the final payment will be equal to the par value plus the coupon payment, so 104. Now the final step is to compute the present value of these future cash flows. All we have to do is to multiply each cash flow by the corresponding present value factor. Then we scroll down, and that's it. So now we have all the necessary data to compute the new actual price for bonds A. So the new price for bond A is the sum of all its present value future cash flows. So 98.2 $206. Remember that the previous price was equal to $100, which means that there is a price change, a percentage price change for bond A equal to the new price minus the previous price divided by the previous or the initial price. So we can convert it into percentage. See here? So the price change is negative, and it was expected since the yield has increased and since we have an inverse relationship between the yield and the bond's price, right? So this is for bond A. Now we repeat the same thing for bond B. So bond B so for bond B we have the coupon rate of, I think, 9%, right? Now the new yield to maturity has become equal to 9%. Maturity are 5 years. That can be converted to 10 periods, and par value equal to $100. Now for the bond B there is no need to repeat the table, right? Because since the new yield to maturity becomes equal to the coupon rate, this means that the new current price of the bond B is equal to its par value, since the bond is offering the same rate than the remaining bonds of the market, right? So the new price of B is equal to its par value, $100. Remember that the initial price of B was 104.055, 104.055. Then the percentage price change for B is equal to the new price minus, see, the initial price divided by the initial price, and then we transform it into percentages. See, so the same thing is also relevant for bond B. Due to this increase in yield to maturity, the price of bond B has dropped down by 3.897%, and we clearly see that the price change in bond B is much higher than the price change in bond A, and this was expectable since the bond B has a higher maturity than the bond A, see, and since the bond B is paying a higher coupon rate than the bond A. So these two things, or will lead to a higher volatility for bond's price for bond B more than the bond A. So that's it for the question number 1. So we'll save it later. Now let's move to the question number 2. Now let's move to the second question. Using duration, estimate the price of the bonds for 100 basis point increase in interest rates. Now we are trying to measure the percentage price change of the bonds following this 1% or 100 basis point increase in in yield to maturity. So we have done this using the present value technique during the first questions, and we found that for 100 basis point increase in the yield to maturity, the price of the bond should decrease by 1.794%. Now we are trying to do the same thing but using the duration technique, right? So these are the required steps. First step, we have to compute the Macaulay duration, then the modified duration, then use the modified duration to have the approximate percentage price change, which is minus the modified duration times the variation of the yield to maturity, right? So these are the steps that we have to follow in order to answer the question number 2. So let's go to Excel. Sorry. So we have a new sheet called question number 2, and we start by the bond A. Remember that the yield to maturity was equal to 8% before the increase, which means that we can convert it into 4% semi-annual yield to maturity. The number of periods in years, 2 years, that can be converted into 4 periods, right? Also, we have a coupon rate of 8% that can be converted to 4% semi-annually, on semi-annual basis. So these are, and don't forget the par value is equal to $100, and the current price is also $100, right? So these numbers are for annual basis, while these ones are for semi-annual basis. Now let's check the formula for the Macaulay duration. So this is the first step, the Macaulay duration. We need the periods, we need the coupon payments, we need the yield to maturity, we need the final period, the final payment, which is the par value payment, see, and the final present value factor, and the current price of the bond, right? So let's build a table to the Macaulay duration. So we'll start by periods, then we have the coupon payment, then we have the present value factor, which is 1 divided by 1 plus y, power the period, right? So let's start by this one, or maybe we can add a new column, which is for this expression c divided by 1 plus y power t. So tc divided by 1 plus y power t. So we have, don't forget, 3 periods here. Sorry, what about that? And 4 periods. Don't forget, for the coupon payment, it's equal to the coupon rate times the par value, which is 4, and this amount will remain constant. Now the present value factor is equal to 1 divided by 1 plus the yield to maturity 4% power the number of period. Remember, because the yield to maturity is constant, so we should add $sign in the formula. Then we scroll down. Then we compute this first term, tc divided by 1 plus y, power t equal t c divided by 1 present value factor, and we scroll down. Then we have the power value, and we have the n m divided by 1 plus y power n. N is the final period, which is equal to 4 for this example. So the power value will be received by the end of the 4th period, and we should have n times m times the last present value factor. Now, to have the Macaulay duration, we should sum up these 4 cells, then add this one, and divide the whole thing by the current price of the bond. So the Macaulay duration is equal, so open the parenthesis, the sum I should move to this is Macaulay duration should equal, and open the parenthesis, the sum of these 4 cells, right, plus this one, and the whole is divided by the current price, and it is equal to 3.77509. Remember, this is the semi-annual Macaulay duration, and it has to be converted to the annual Macaulay duration. So the annual Macaulay duration. So all we've got to do is to divide this one by the number of periods per year, which is 2, divide by 2, and we got the annual Macaulay duration. Then the next step, we have to compute the modified duration. So the modified duration is equal to the annual one divided by 1 plus the yield to maturity, 1 plus the yield to maturity. This is the modified duration. And finally, the percentage price change, because we are asked to find the estimate of the price of the bonds change, right, for 100 basis point increase in interest rates. So this means that the price or percentage of price change using duration is equal to, see here, minus the modified duration times the variation of the yield. So minus the modified duration times the variation of the yield, which is 100 basis points or 1%. 1%. So this is the price change using the duration. So this means that the bond's price should decrease by 0.0181495 for every 100 basis point increase in the yield to maturity, right? So let's transform it into percentage. So this is the price change estimate using the duration technique, right? Remember, the real price change was equal to, see here, minus 1.7938, while the estimated one is 1.81495. So this means that the new estimate bonds price should be equal to the initial price, which is 100, see, times 1 plus the variation. So this is the estimated new price, 98.185. While using the present value technique, we find that the new price was equal to 98.206. So there is a difference between the new or the two, two techniques. So for the present value technique, the new price is equal to 98.206 following an increase of 1% in the yield to maturity. While using the duration technique, see, so this is the estimate, right? So this is the observed one, this is the estimate. So there is a gap between our estimation and the real observation, right? And we'll see later that the reason of this gap is the convexity of the curve, and we'll see that we have to add what we call the convexity measure in order to correct or to fill this gap and make the estimate closer to the real observation, right? So this is for the bond A. Now we do the same thing for the bond B, see? So in order to save time, I will not, expose all the calculus for the bond B, but you will find it, in the Excel file that I will send you later on by email, inshallah. This is, for bond B, right? We have found a Macaulay duration equal to 8.30838. Then we converted this Macaulay to annual Macaulay duration. Then we have computed the modified one, and finally we found the price change or the estimated price change using the duration technique. See, so we have here minus 3.9944%, right? While when we refer to the present value technique, the price change should be equal to minus 3.897. So once again, there is a gap between the real price change using the present value technique and the estimated one using, the duration technique. So the reason of that gap is the following. We have the convex curve, see? So this one is the curve that retraces the evolution of the bond's price following an evolution of the bond yield. So we can clearly see here the inverse relationship between the yield and the price. Every time the yield is going up, see, the price is going down. Now the problem is that this decrease of the bond price is not linear, it is convex, right? This means that the slope of this decrease is not constant, it varies actually. Here, when the bond yield is too low, the variation or the decrease is too high. The slope is very high, right? Actually, it is like 100% here. While when the bond yield becomes too high, the convex almost, or the curve almost becomes flat, right? Which means that the slope is very close to 0%. So this is the problem, that the curve is convex. And see the line here? So this is the estimated price of the bond using the duration technique. So we have a tangent, a linear tangent to the curve. So when we have here the tangency point, so we'll find the same result whether using the present value technique for the convex curve or the duration technique for the linear tangent, right? Now the problem is, or the thing gets worse when we move away from this tangency point, right? Every time the bond yield change becomes larger, see, the gap between these two, between this convex curve and this linear tangent becomes larger, right? And this gap is due to the convexity of the curve. So when the bond yield is too high, we have an overestimate of price decrease when the yield rises using the duration technique. Now, when the bond yield goes to the other side, which means that when the bond yield decreases, we have an underestimate of price increase using the duration technique. So in order to fill this gap, we add a new measure to the duration measure. This new measure is called the convexity measure. When mixing both of the duration and the convexity measures, we should get, or should have, a new estimate closer to the real new price of the bond. And we'll check it out right now by answering the question number 3. So let's get back to the PDF file. Now, using both duration and convexity measure, estimate the price of the bonds for 100 basis point increase in interest rates. So let's open a new sheet and call it question 3. As usual, we start by the bond A. Now, for the convexity, the following steps are mentioned here, right? See, so the convexity measure is equal to the second derivative of the price of the bond to, the yield to maturity times 1 by P. So the second derivative is equal to the sum of T by T plus 1 by the coupon payment divided by 1 plus the yield to maturity power T plus 2 plus N times N plus 1 times M divided by 1 plus Y power N plus 2. So it is a little bit complicated compared to the duration, the Macaulay duration formula, see? So for the second derivative, we need the t plus 1, and even for, the present value factor, we no longer use power t, but t plus 2. Same thing for the final payment. We add a new term, which is n plus 1, and we add plus 2 here for the yield to maturity. So let's build a new table for the convexity measure of the bond A. Okay, so we have a yield to maturity. Annual one is 8%. That should be converted into semi-annual one by dividing the annual one by 2. Then we have a coupon rate. The annual one is equal 8% also. It becomes 4% on a semi-annual basis. And we have number of periods. There are 2 in terms of years and 4 in semi-annual basis. And finally, first we have a par value of $100 and the current price also of $100. The first column for periods, then, or let's call it T directly. Then you have the T plus 1. Then you have the coupon, then 1 divided by 1 plus y power, not just t this time, but t plus 2. Then we have the t times the t plus 1 times the c divided by of this expression. Then we have the par value, and finally n times n plus 1 times m divided by 1 plus y power n plus 2. Okay, so we have 1, 2, 3, and 4 periods. Now I have to transform this 1 to t plus 1, so equal t plus 1. Let's scroll down. Now the coupon payment is equal to the par value times the semi-annual coupon rate. Since both of these two variables are constant, so we add the dollar sign, then we compute the new present value factor. Now you have to pay attention, it's power t plus 2, right? So equal to 1 divided by 1 plus the yield to maturity power t plus 2. Now since the yield to maturity is constant, we should add the dollar sign. Okay, now it is equal to t times t plus 1 times c times the new present value factor. And we scroll down. The par value is 100 received at the final period equal n times n plus 1 times the final payment of the par value times the present value factor for the final period. Now the second derivative is equal, see, so the second derivative to the sum of the cash flow related to the coupon plus the cash flow related to the final payment. So equal to the sum of these four cells, right, plus this one. This is the second derivative. Then the convexity measure is the second derivative, see, divided by P, which is the current price of the bond. Now, before proceeding to the convexity measure, we have to pay attention. This one, or the second derivative, is on semi-annual basis. So I have to transform it into annual basis. So the annual second derivative equal to the semi-annual one divided by the square of the number of periods, which is 4. Before proceeding to that one, so we should first compute the convexity measure. It is equal to the second derivative divided by the current price now we move to the annual convexity measure. See, it is equal to the semi-annual one divided by the square of the number of periods, 4. So this is the annual convexity measure. See, and so this is the annual convexity measure. Now, the price change due to convexity is 1/2 of the convexity measure times the square of the variation of the yield. So the percentage change due to convexity is equal to 1/2 times the annual convexity measure times the square of the yield change. So the yield change is equal to 1. So 1%. So the square of 1%. You can transform it into percentage. So it is equal to 0.02139%. So this is the percentage of change due to convexity. Now, the global estimate of the percentage of change of the bond price so it will be equal to the price, or sorry, the percentage change due to convexity, this one, plus the percentage change due to duration, see, for A, sorry, so this one, for A, is equal to minus 79356%. So this is the estimate of the percentage change of the bonds price using both convexity and duration. Now let's compare it to the real percentage of change that we have computed using the present value technique. Now the real percentage change of the bonds price, so it is equal, so this one in question 1, and let's transform it into, see, so almost we have the same percentage of change. It's very close. So the difference between the estimate and the observed change, so the difference between, let's say, the real and estimate percentage change is equal, so the real one minus the estimated one, something like 0, right? So this is, or this proves the the efficiency of the fact to add convexity measure to duration measure in order to have a more accurate forecast, right? So we do the same thing for the bond A, right? And we should have the same result or same interpretation, that by adding convexity to duration we will be able to improve in a substantial manner the accuracy of our estimates. Bond B, right? So we'll use the same technique, except that now we'll have to treat with 10 periods instead of 4, right? So these are the second derivative, the convexity measure, the annual convexity measure, and the percentage change due to convexity. Now if we add this percentage change due to convexity to the percentage change due to duration, the global estimate is equal to minus 3.8956, which is very close, see, to the real percentage change. So the difference between the estimate and the real one is equal to just 0.00138%, which is, when we transform it into numbers, it becomes, say, 0.0000014, which is very, very small difference, right? So by adding, once again, by adding the convexity measure, we are making our estimate more accurate and more close to, or closer to the reality, or the observed price change. Now let's go to the next question. Comment on the accuracy of your results in part B and C and state why one approximation is closer to the actual price than the other. So we already talked about this question. So by adding the convexity measure, we are making our estimates more accurate than the case when we just used the duration measure. And this is due to the fact that the curve is convex, and by adding the convexity measure, we are filling this gap between the linear tangent line and the convex curve. Now the E, without working through calculations, indicate whether the duration of the two bonds would be higher or lower if the yield to maturity is 10% rather than 8%. So the accuracy of the results are actually will diminish every time the price or the yield change becomes higher. So for the B and C question, we treat a change equal to 100 basis point, right, in the yield. Now we are talking about 10% rather than 8, which means 200 basis point. So every time we are going too far, we are making the yield change too big, this will lead to a less accurate estimates using the duration. And if we look to the graph here, you see, so every time the bond yield is going up, right, we are overestimating the bond price using just, the duration technique. So with 10%, the price of of the bond, or the estimated price of the bond using the duration technique, will be overestimated. All right, so this is the answer to the question 4. Okay guys, that's all for today. I hope you'll find this video useful, and I hope it will help you improving your understanding of the convexity and the duration concepts. So please feel free to contact me should you need any further information, or should you have any further questions. Don't hesitate, please. That's it. So see you next week, inshallah. Bye bye.